I'm looking at some additional properties of complex numbers. And let me refresh your memory a bit that if we have a complex number here, usually represented using the symbol z, it has a real component, and usually the real component is represented as being on the horizontal axis, and has an imaginary component, um, sometimes represented by IY. We write the complex number z equal to x plus I times y. Okay, now um, the so here's a point, let's say, in the real imaginary plane. We represent the length of the complex number, or the magnitude of the complex number, as geographically as being the length of this green line right here. Now, we can actually compute that by looking at this right triangle right here, where this x horizontal dimension is x, the vertical length is y. So using the Pythagorean theorem, we can say that the magnitude squared of the green line, or magnitude of z squared, is equal to x squared plus y squared by the Pythagorean theorem. Then we take the square root of both sides. We have the magnitude of z, or as we call it, the length of the complex number, is equal to the square root of x squared plus y squared. So this is called the magnitude, or the modulus, of the complex number. Okay, the modulus or magnitude. Okay, now a second concept which comes in quite handy, and you'll see that as we move along. But the second concept I want to discuss right here is called the complex conjugate of a complex number. Again, if the complex number is written as z equal to x, the real part, plus I times y, the imaginary part is iy, we write the complex conjugate, and sometimes I just call it the conjugate of the complex number, as z asterisk is equal to x minus iy. So the real part of the conjugate stays x, but we switch the sign of the imaginary part of the conjugate to negative iy. Now, what this means then is if we use the conjugate and we compute the product of z times the complex conjugate of z, or z times z conjugate, like this, what we have is the following expression. We have x plus iy, and then multiplying this times the conjugate means we have x minus iy. So x plus iy times x minus iy, when we multiply this out term by term, we get this is equal to x squared minus I times xy plus the I times xy comes when we multiply this times this. Then we have a plus iy times x, which I'll write as plus I times xy. And then we have this term, which is iy times negative iy. Now, I times I is negative 1, because I is the square root of negative 1, if you remember. So I times I is negative 1, but then the negative of that becomes a plus 1, so we add a plus y squared that comes from the product of this term times this term. So now let's combine these terms and reduce the expression. We get x squared plus y squared, and then the negative ixy cancels with the positive ixy. So we have then that z times z conjugate is x squared plus y squared. But if you look over here at this expression right here, this is equal to the modulus or magnitude of the complex number squared. So this is our important result, and this is usually how we compute the magnitude of the complex number. We compute it by using the fact that z times z conjugate is equal to magnitude of z squared. Okay? Another important result, more to come.